Welcome everybody to this COMSOL Multiphysics tutorial where we'll be setting up a fluid dynamics simulation for our Ahmed body. So the first thing we're going to want to do is go to the model wizard. We will be working in 2D only, so select 2D. Then we will be going down to fluid flow, then single phase flow. We're going to find turbulent flow, and then we're going to go for this one right here, turbulent flow K epsilon, because we're going to be working with high Reynolds numbers. So double click on that. Then click study and then select a stationary study. This is from another project, so don't worry about that. Okay, so now that we're in, we're going to start off by building the geometry for the vehicle. So in order to do that, we're going to have to first set up some parameters. So I'll put them up on the screen, copy them, and we'll meet back here. Okay, so now that you've copied all of these parameters right here, we are ready to start defining the geometry of the car. So we're going to go up here to the geometry toolbar, and we shall be doing this in sketch mode. First of all, make sure that's selected, and then we're going to click on polygon. Okay, so the first thing we're going to do is we're going to define the starting point. So the starting point is going to be the left vertex of the car, and that's going to have an x value of 0 and a y of wh, which stands for the wheel height. That's our first point. Then our second point is also going to have 0 on here. It's going to have a wheel height plus the grill height. Then our third point, is going to have a bonnet length for the x. And then for the y, it's going to have the same as before, so the wheel height plus the grill height. Then if we build the selected objects, we're going to see that we have this. Now what we need is another point, which is going to compose our windshield. So at this stage, we're going to need the bonnet length plus the windshield length times the cosine of 50 degrees. Then for the height, it's going to be similar to before, so we're going to have the wheel height plus the grill height plus the sine of the windshield length. So we'll have something that looks like this. Now we need another vertex that's going to go here on the right, which is going to complete our roof. So for this, we're going to have one entire car length for the x, and then a height which is going to be the same as the one for the point we just described before. So something like this. If we build the selected, we'll see that we're almost there. Then for the last point, which is going to be here, that's going to have an x value of the car length, and it's going to be at the wheel height. So with this, we have defined our Ahmed body, and it looks pretty good. It looks pretty nice and solid, as you can see, because we're still in sketch mode. No solid has been formed. However, the type has been set to solid. Now, what we're going to do is we're going to build a rectangle, which is actually going to be our wind tunnel. So we can call this wind tunnel. Here we go. And it's going to have a width of 8 times the car length. It's pretty standard by literature. For the height, it's going to have 2 times the car length. Again, this is supported by literature. Then this, the position, we're actually going to use minus INL. And now if we build the selected, as you can see, we have our wind tunnel, and it's also, we're all still in sketch mode, so it's going to look like this. Then the thing that we need after is actually to get out of sketch mode, and as you can see now we have actual solid objects, and we're actually going to use a boolean, and it's going to be a difference modifier. So what we're going to do is we're going to add the rectangle, and then we're actually going to subtract this object right here, just like that. And as you can see, this works quite nicely, because now what we're going to do is we're going to define the flow, the fluid inside of the of this entire container, and then we're just going to have a cutout here, and this is computationally a lot more efficient and also gives us more control over the mesh, because we can define it using box refinements, but also, as we shall see later, it's just a much cleaner way of doing it. You also don't need any extra materials. You can just work with the air itself, and then you don't have any weird things happening with that. However, in reality, Something that you could want to do, because it does make a big difference, I've realized, is adding a fillet. So what we can do is we can go back into sketch mode. We're going to disable this modifier here, because right now, um, when that is enabled, essentially you have already built your solids and you can't modify those. So what we're going to do is we're going to leave that. We're going to go back into geometry. We're going to go into fillet. We're going to put the fillet above the difference modifier, and then we're going to select all the edges. You don't have to select all the edges, but I'm going to select all the edges. So if you go up here to this button, you can create a selection box. You can click and drag, and that will allow you to select everything you need. So let's do that again. Let's select all the vertices. There you go, the vertices have been selected. Now you can build all the selected, and oh yeah, sorry, I need to set your radius for the fillet. So in the manual it said that it has to have a maximum radius of 0.01 meters, which is what we're going to use. And now you can build the selected, and you won't be able to see a difference, but that's only because we're too far essentially from the model. So if we zoom in, we can see that we have created a fillet right here, and all of the edges are like this. Essentially, we have smooth edges now, and this prevents errors in computation, especially when we're looking at the stress. You don't get any what are they called, singularities on the edges. So having done that, we can go back to the difference modifier. We can enable that, and we can build all the objects. We leave sketch mode, and as you can see, now we have a nicely defined geometry, including these fillets. Let's just check that they're there. Yep, you can see we have smooth edges now. So that is basically everything that we need in terms of the mesh itself. That part is completed. Now what we're going to need is a material as well. So if we go up here to the materials, we can click add material. Then we go to built-in, we let it load, and then air. So essentially, yes, here we go. Now close the tab. And COMSOL has done that for us already. It's given our domain here, because now we only have one domain really, which is the wind tunnel itself, and it is air. It's got all your parameters. Then here we can go into turbulent flow, and here essentially we have all the parameters that we need to define the flow itself. So the first thing that we're going to need is to define an inlet. So double click or right click on turbulent flow. Then we're going to add an inlet, and we're going to select the leftmost boundary, although you could select the right one if your vehicle is turned the other way. Sorry, yes. Then what we're also going to do is we're going to set an initial velocity. So here under velocity, we can type in u in, which is, if you recall, is our parameter for the initial velocity of the wind. Then again, we can go to turbulent flow, double click or right click, and then we also going to need an outlet. We're going to select the rightmost boundary, make sure that the pressure is static and is set to 0. That's fine. Then for the walls inside of the tunnel, these are our walls essentially. They comprise the vehicle itself, or the cutout of the vehicle, and these walls as well. And we're going to apply a slip condition, essentially lowering the, I'm pretty sure it's the effects of those walls. Essentially, the air won't stick to it as much. That being said, we're going to go back to the turbulent flow, and this is really a preference, but I'm going to include gravity in the simulation. So all you have to do is tick this box, and you're going to have gravity. This is set to Earth's gravity, so you don't need to mess with it further. Then once that's done, here you can see that we have a normal mesh essentially, but we don't really want that. We want a little bit more control over the mesh, so we're going to right click on the mesh. We're going to click free triangular. Okay. Then we're going to set it to a domain, and we're going to click here to select our domain for the wind tunnel. Okay, perfect. Then we're going to right click on free triangular 1 and click on size. Then we're going to calibrate this for fluid dynamics, and essentially using this tab here, you can set the size of the mesh. We're going to go for a coarse mesh because it's actually a pretty, as you can see, even with coarse, it's quite defined already, close to our vehicle, as you can see here. It's very well defined. But if you wish to have more refinement, then what we can do is we can use a box refinement. So what we're going to do is we're going to click on mesh 1 again, right click, then modifying operations, and then refine. Number of refinements, I found that 1 worked out pretty good. So what we're going to do is do it in a box. So we're going to specify a bounding box. And for this, essentially, we're just defining 2 vertices that form a rectangle. You can imagine one vertex here and then another one here. And essentially, they're going to form a rectangle, which is what we're going to define with. And we can use some of the parameters that we defined before. So for example, for the x, we're going to set it to negative front padding. Front pad, this is the padding that we have set as our parameter. Then for the back, we're going to have the car length plus the back padding. For the y, it's leaving it at 0 is fine. And then for the top padding, we're going to have the car height plus the top padding, like this. Now if we build selected, you can see that we have defined, and if we zoom up back here, now as you can see, we have defined this little box here. And you can tweak these parameters if you want, but I found that the versions that I gave it right now, the values I gave it right now, are pretty good. So that is pretty much it in terms of refining the mesh around the vehicle. And at this point, we are ready to compute the study. So we go to study 1 and we click compute. And now we wait. Okay, now our computation is finished, and as you can see, we have a cool little plot here. If we zoom to the extents, we have our entire wind tunnel. As you can see, the wind is coming in from the left, striking the vehicle, and slowing down, essentially, especially here at the boundaries and back here. And there are a couple of things we can do to enhance the quality of this plot. So for example, if you go over here to the velocity, we can actually add, and right click, we can add a streamline plot. Then what we're going to want to do is on the selection, we're going to have to click all boundaries. And for the streamline positioning, we're going to change the point distribution to mesh based. And then we can add, I don't know, for example, 3 mesh refinements. And then if we plot, here we can see actually the behavior of the air in terms of contour lines. So for example, here behind the vehicle, we're getting a lot of vortices formations, essentially, caused by the geometry of the car. It's this 90-degree angle that causes these, I'm pretty sure. So, yeah, this is what it looks like if we zoom out, but if we go close to the vehicle, it actually tells us a lot about how the air is behaving around the vehicle. So, that's the first thing. Then the second thing that we're going to want to do to actually calculate the coefficient of drag is we're going to go up here to results in the toolbar. Then we're going to go to numerical, more derived values, and we're going to perform a line integral around basically the entire boundary of the car that forms the car. But there's something that we can do right now which will make our life a lot easier in the future, and that's make pre-selected boundaries selection, essentially. So you'll see what I mean. So if you go over here to data sets and we right click, what we can do is we can click on Edge 2D, and essentially what this is going to allow us to do is make a selection that we can later use for the plots. So once we're here, check that the data set is indeed pointing towards study 1 solution 1, because that's where it's going to that's where it's going to evaluate the expressions, essentially, on the given boundaries that we're going to give it right now. So we're going to go over here, and again we're going to use our select box to make sure that we have all the vertices. If you were to do this by hand, you would run into an issue which could take you hours to fix. That's what happened to me, and it's that the fillets that we added before have created their own little boundaries, and you need to include those boundaries, otherwise you're going to get some really weird behavior when you evaluate the expressions at the corners, and trust me, you want to avoid that. So we can give this a nice little label, something like car boundaries, like this. And now we can go back to the line integral, and for the selection, for the data set, we're just going to click on car boundaries. And because the car boundaries here already have the data set as solution 1, we don't need to worry about that anymore. So we can go back to line integration, and now we're actually going to write the expression that we're going to evaluate. So essentially what we're using is the raw formula for the coefficient of drag, which is 2 times, and bear with me here, SPF dot T underscore stress x. Now what this weird looking expression means, SPF is the way that you're evaluating the expression, I'm pretty sure. T stands for total, and then underscore stress, x, is the total stress in the x direction. Then what you're going to want to do is divide that by rho, which is the density of air, and multiply by the square of the inflow velocity, multiplied by CH, right? The car height? Yeah, that's it. Make sure that the expression is unitless, so it has units of 1, and that should be correct. Then for description, we're just going to write CD, that's the coefficient of drag. And then down here, we're just going to type in SPF.T underscore stress X just to evaluate what the stress is by itself. As you can see, we have units of newtons per meter, which makes sense considering that we're in 2 dimensions. And now we're going to evaluate the expressions. And as you can see here, we have a coefficient of drag. The reason why it's negative is because the stress is also in the negative direction overall, since the air is going towards the right. So naturally, the stress is going to point towards the left if given the boundaries. And that's how we calculate our coefficient of drag. Now, to generate the plots that we want to that we're asked to generate in the exercise, what we're going to want to do is we're going to right-click on results. We're going to click 1D plot group. Once that is done, we're going to see that we have a nice little plot set up here, but we are not plotting anything yet. So we're going to go back to 1D plot group 4, which is the name that COMSOL has given this plot, and we're going to add a line graph. So essentially what we have, and as you can see here, the data set says from parents. So what we're going to want to do actually is go here to the 1D plot group and change the data set to the car boundaries. So we're evaluating just as we were before for the coefficient of drag. We're going to evaluate just along the car boundaries. So now, as you can see here, line graph, this is also pointing now towards the boundaries. And here what we can see is that COMSOL has generated a plot, and this is just the velocity of the air particles on the boundaries. But this is not something that we care about. So the first thing that we should do, that we're going to plot actually, is the total stress. So let's give this a nice little label, total stress. And what that means is that the expression that we're going to evaluate is going to be SPF, just as we did before, T underscore stress X. Our units have changed, as you can tell. And now if we plot once again, we're going to get this cool looking graph. And this is essentially the total stress along the boundaries. It's pretty cool looking, but I don't like how this looks. So for the legend, yeah, we'll fix this in a bit. But anyway, this is the total stress, and now we're going to repeat the same thing for the viscous stress. So we're going to right-click on 1D plot group 4. We're going to click on line graph once more. We can call this viscous stress. And then for the expression, now it's going to be K underscore stress X, like this. And we can plot this as well. As you can see, the viscous stress is behaves very similar to the total stress, except that it's a lot lower in magnitude usually, is what I found. Then the final thing we're going to want to do is, again, add another line graph. And now we're going to evaluate a new expression, which is pretty cool looking, SPF dot NX mesh. And essentially, these are just the normals in the X direction for each point in your mesh, times P, P being the pressure. Let's give this another label. We can call this total pressure in X, and we can plot this as well. And as you can see, we get a cool looking graph that looks just like this. The total pressure and the stress behave very similarly. It's just the directions are opposite. But now let's make this graph. We can make this graph look a lot better. So if we go back to 1D plot group 4, we can call this something like exercise plots. I don't know. You can probably think of a better title. And what we're going to want to do is change the x-axis label from arc length to something like car boundaries, like this. Then we're also going to show the legend. That's fine, but now we're going to have to change all the individual legends. So here, if we go to the total stress, we can click on legends. We want to show the legend. We don't want the solution, but we do want a label. And we're going to do that for all the plots that we generated, like this. Include the label, deselect solution, show legend, and essentially we're going to have a nice nice looking graph like this. Mine looks a little weird because I made the font size bigger so you guys could see better, but this is essentially what we have. And yeah, we should change this title as well, so we can go over here, we can put the title um, to the label, and we can get a cool looking graph like this. And essentially this is it. These are the plots that you need, and if you look at them, they don't really make intuitively that much sense in the sense that you can't really picture it in your head, but that's only because we're looking at the car boundaries of the entire car. If you were only to do the same thing for the top of the car, you will get a segment of this entire graph, but probably only this segment here. Anyway, what I mean is that if we go to, for example, here, so we can see our vehicle, we're looking at all of the edges. So it's kind of hard to imagine what is happening at each of the edges. But for example, with respect to the stress, what you're going to find at these vertices is that, for example, here, the air is going to hit this boundary and it's going to experience the stress in the negative direction until it gets to this edge, and then there's going to be a tip-off point where the stress changes direction and it's going to go in the positive direction, and then it's going to essentially go to 0 here when the surface is perpendicular to the, parallel to the direction of the flow. And that is why you're going to have these spikes here. All these spikes are usually caused when there is a boundary or where there's a fillet. Anyway, so where there's a vortex or where there's a fillet. The fillets usually make the effects less anomalous because, you know, the flow can just bend around and it doesn't hit a hard edge. But generally, that's what these big points mean, that the air is encountering a sharp change in the geometry of the car, which, you know, makes sense. And yeah, that's basically it. Then what you can do if you wanted to improve the design of this Ahmed car, which is pretty boxy looking, is instead of just constructing a regular polygon, you can go back to geometry, enter sketch mode, and again disable the difference modifier. So we can disable this and build all objects. Actually, wait, I think you need to deselect the fillet as well. Yes, okay, deselect the fillet as well. And now essentially what you can do is you can just move these vertices around. But the cool part is that, for example, if you can go up here to draw quadratic, you can just draw a quadratic. So if you click here, then click here, essentially what you have are handles, which you can later right click, finish quadratic Bezier. And then essentially what you have is a topology that you can just manipulate independently of the other points. So for example, if we wanted a smooth edge here at the front, we could just add this as like such. Move this quadratic Bezier up here to so it's next to the polygon, just so we don't get confused. And then essentially you repeat the same process, add in the fillets at all the vertices. So you have to, you know, go over here, enable this, do a box selection of all the vertices to make sure that these edges, that these points here are smooth and they're not super jagged, because they're actually very jagged. If we look here, we want to make this as soft as possible, because it will make actually quite a big difference, especially because our mesh is so fine. So you're going to want to do that, and then again apply, get out of sketch mode, and then once you have solids, apply the difference modifier, and then just repeat the process. But it's pretty good workflow, I found, for changing the topology. It doesn't take that long once you get used to it, but it will take some getting used to. Yes, and then again for the car boundaries here, I created the selection which is all the boundaries, but you could create another thing. So if you go here, right click on the data sets and click another edge 2D, for example, you could create here we make a box selection here like so. So now we've only selected all these boundaries, including the fillets here at the edges. And yeah, basically you could create another 1D plot group which only evaluates from the top of the profile of the car, for example, which is also quite nice. But yeah, that's pretty much it. So I hope this tutorial was useful, and if you have any questions, please comment down below. Don't forget to like and subscribe for future uploads.